Hi, everyone. I'll present myself a little bit before I talk a little bit about the intersection between AI and the brain. So I got the privilege to touch both fields. In my master's degrees, I did brain science in Tel Aviv University, and Ichilov, I did research around fMRI and build classifiers around those areas to try to predict if someone did something or did not do something in the year 2008, 2009. Back then, these kind of areas were pretty new. After that, I opened a startup in what was early data science. AI was not very popular in 2009. We sold it to Salesforce.com. I was chief data scientist in Salesforce. We brought Salesforce to Israel. We opened the Israeli branch. And 2015, when my vesting ended, I traveled the world a little bit and thought about what could be interesting to do as the next thing. Mainly thought about what would be the biggest thing that would happen next. And something that was pretty big back then, and we'll talk about it a little bit, is the area of deep learning and vision. And I actually, by accident, found a professor coming back from Stanford to lead the NLP efforts in Tel Aviv University. And he kind of did a quick seminar, a first seminar. And one thing he said, is that there's another professor called Michael Jordan. It's not the same Michael Jordan. But he's also very well known in the field of machine learning. And he said in 2015 that there's a problem in the field of semantic parsing, that if you answer just a natural language question, like what is the second biggest city in the US that has a river next to it, that kind of question, those kind of answers would be worth billions of dollars in the future. And for an entrepreneur like myself, that rings a bell. And I got really interested in that field. My PhD, I was first PhD with Jonathan. It was around reasoning for question answering. That's pretty much what ChatGPT did, and we were fortunate enough to see this whole revolution unfold between 2016 and 2020. We even got some best papers with Google and OpenAI. And in 2020, we realized something big is going to happen beyond academia. LLMs were already out, generative AI was already out. We'll talk a little bit about that. And we figured we'd open a solutions company in the field of AI. We brought some PhDs and professors, but you all know foundational model companies today like OpenAI, Cohere, and Anthropic. That demands a lot of funding, as you can see today. And we figured that there would be another branch that we talk about later about enterprise AI that would be more of a solution layer to try to change the way we work. And that's why what Ask AI does today. We're 40, 50 people, A-round company, and pretty much helping employees and enterprises. And I'll talk in the end a little bit about what we do. So that's kind of briefly about my intersection between AI and brain science. And today I wanted to talk about kind of what's the relationships between those fields and many kind of dimensions, both how brain science inspires AI, how AI helps with brain science today, and how both can help each other with building better tools, and what analogies in terms of how AI does things we now know that are very similar to how the brain does it and vice versa. So we'll start with one quotation about kind of the history between the relationships of machines and the brain. So Dijkstra in the past said that the question of whether machines can think is about relevant as the question of whether submarines can swim. What he meant is that machines that we built in the past were nothing like the way we do things. So all the machines, if we built like machines for making cloth, machines for typewriting, machines for any kind of machine we built in the past would never do that kind of action similar to how humans would do those actions. And that didn't stop kind of with early machines. It even continued with kind of early computers. So computers before AI are nothing similar to how our brain works. Their memory is very different. It's way, way more accurate than the human brain. The speed of the networking and the speed of calculations is very different. And so even with the first computers, it was nothing like how the brain does these things. It just helps us, and the function could be a little bit similar, but it doesn't do the same things as the brain. The one exception is what we see and call today AI. When you say to people AI, they all think about how humans do it. Speaking like a human, even walking like a human. doing everything pretty much like a human and also augmenting how we do it. Today, we want AGI to be kind of better than how we do things, but still, we expect it to communicate with us and think the way we think. And so today I wanted to actually cover a little bit about what we know on different kind of functionalities of the human brain and compare it to what we know in AI. From vision to memory to imitations to motorics, any area, we're going to cover each one of them and talk about what we know about the brain there and how AI does it today and what's the gap, and does the AI come close to how the brain does these kind of things today. So let's start with vision. It's not a coincidence that we're actually talking about vision, because vision is one of the pivotal changes in AI. It kind of moved us between AI that can, win computer games like chess in 1996 to AI that can really do something that's useful for us. So for the first time, computer vision was able to autonomically ride a car. Here you see just a film from Mobileye that uses a camera and uses computer vision to steer a car. But today, that kind of technology is very wide used. And so why I'm showing this first is because vision was the first kind of revolution in deep learning. Deep learning, we used to use neural networks in a kind of very shallow way. And with deep learning, it brought us to a whole new level. And so just to talk about a little bit before we talk about how deep learning works, I always want to show the difference between what we're actually building and how the brain does it. Humans tend to use always all their context, multimodality, and all their knowledge. So if you have this kind of circle, I'll stop the video. What do you think a self-driving car should do in this kind of situation? What would it do? You see this kind of circle, you see kind of a dashed line, and so what should a car do in this situation if it's routed to go in the circle? What do you predict it would do? Okay. And why would it stop? Because we all know that when you draw that kind of line, you cannot pass, right? And so if a computer should do these kind of things blindly, then that would be the result. But with humans, that's not the result. So humans apply all their, what we call common sense, all their knowledge about the world to every task they do. And that's what we expect AI to do. And that's why each time we see such a situation, we always laugh, say, oh, this computer is pretty stupid. Why can it figure out that this is not real, right? So that's true for AI even today. As we approach general kind of artificial intelligence, we expect it to be very multimodal. But even 10 years before, it was not even close to that. And you can make every AI fail in certain ways, and we'll show different ways to make AIs fail, even though people spend billions of dollars creating this technology. A little bit of what we realized made all this possible. I used to have a professor in my second degree called Chazi Shurun from Tel Aviv University, and he always said that neural networks in 2008 are second best to everything. Like they would do any task second best. But in 2011, that all changed. We realized that if we have enough examples to train a neural network, and we have enough computer power, then it was kind of the first GPUs, we can actually train them to do amazing stuff. So ImageNet was the first kind of challenge in which they were able to get enough data, 14 million examples, and train a deep learning network to be able to classify images. Until then, humans would do it about 91% accuracy. The classification should be what exactly are the species in the image and what type of species. And machines would do it about 10% less, 81% accuracy. And when deep learning was introduced, then that was the first time in which computers passed the human. And now it's about 98%, I think even more. And so how is this possible? So I know there's some people that are very technical here and know how neural networks work, but maybe I'll explain. a little bit about the intuition around it. So neural network are not like programming. You don't give it programmatic design. It actually learns from examples. That's why examples are so crucial. What it learns is it learns that every time it makes a mistake, an example, it changes something, and that's how it improves, and it does this billions of times. So what you see here is how that kind of autonomous car solves the problem. It tries to classify each pixel in the picture to what type of entity is that. Is it a tree? Is it a road? Any kind of entity there. And the way it does that, we all know that pictures are made of pixels. Pixels are just numbers, okay? And that's the input that this network gets. It gets a bunch of numbers, and these numbers change every time the frame changes, okay? But now these numbers go through layers. The reason it's called deep learning is because there are multiple layers. Again, I'm trying to explain this in very like high level. And each one of these layers have a connection that is called a weight. And the analogy to the human mind is that this is the synapse and this is the neuron, and the weight is kind of how much activation the synapse need to pass the threshold and fire, the neuron would fire. But that's just an analogy. It's not, we all know that's not even close to how the human neuron is much more complex, but the general idea is pretty much inspired by it. And then every time it tries to get the numbers through these weights and just multiply them until it gets to a final number, and the final number should represent the classification, what's in this pixel. So it may, in the beginning, randomly guess it because the weights are just randomly initialized. But once it gets it wrong, each time we show it the correct label, the correct result, and then the weights change just a little bit closer to get the correct result. So this is kind of very high-level intuition about what it means to learn from examples. So it learns from mistakes, but you should imagine that it does this billions and trillions of times. So it does this so many times that eventually it does converge the weights to predict the final output. And for that, you need a lot of examples, and you need a lot of computing power. And this is all that's happening in the field of AI today. All the models they're seeing, including ChatGPT, all the amazing stuff they're doing are a combination of trillions of examples and the right kind of data and a lot of compute power. There's no magic about these algorithms. The models are not magical at all. We're going to see a little bit about the models. They're pretty much all the same, okay? The differences are very small. But if you have enough money to get enough data and enough compute power, you can get even ChatGPT if you want. So let's talk about how this resembles a little bit the brain. So we actually explored what's happening in these weights. You know, we saw layers and then we saw weights. So let's say we give the network a car, and then we calculate what happens when we give it the pixels and multiply by the first layer of weights. We get just lines, you see, in different orientations. But if you look at the second layer, now you're getting shapes that start being more meaningful. And then in the third layer, the shapes start resemble parts of car. Like this is a wheel. You can see all sorts of parts within the car. And so that helps this network recognize if what we're seeing is a car or not. It's trying to match what it's seeing to different kind of shapes that a car should have, okay? And so this is just lines orientation. This is more complex shapes, and these are very complex shapes. What's the analogy to the human mind? Well, it seems that the human mind does something very similar. In the human occipital cortex, it's in the back of your brain, you know, signal comes from the eyes to the back of the brain. There's also layers of neuron. They're called V1, V2, V3, V4. And they do something very similar from experiments that people have done, both on cats in the past, and now they know to do it even with humans to understand that each one of the layers, the first layers know to do kind of orientations of lines, then more complex and more complex shapes, until it gets to areas that are much deeper in the brain that can actually recognize even people or objects that are much more complex in there. And so this is kind of the first place in which you can see a resemblance between deep learning and how the brain works. Another resemblance is what we call today self-supervising. So the whole breakthrough with ChatGPT, and we'll show that later with text, is that you can train these kind of networks with really small examples, and all you need to do is predict the next step, okay? So how does the mind do it? The mind tries to train the visual layers in the visual system by predicting the next step, meaning the mind is trying to predict what it's going to see next. And it does that all the time. And you can see kids staring there trying to predict what they're going to see. That's why when they're surprised, they start laughing. They like to be surprised because that shows errors to the system, and then it learns how to predict better. There's a lot of examples that show that the human mind also trains itself with trying to predict the next step. And when we get to ChatGPT, you'll understand how that exact mechanism works the same with language as well. It's not just with image, okay? Let's talk a little bit about what the intersection between deep learning and kind of researching the brain is. So one of the researchers that was actually before generative AI, but after kind of deep learning, is trying to predict what a human is thinking. This is not very new anymore. It's about 7, 8 years old, these kind of ideas, but you can do this even with an fMRI today. You put a scanner, and the scanner tries to scan the human mind while it's looking at pictures. And what it's trying to learn is what is the human actually seeing. So it's trying to compare what the brain activity is with the image. And it's trying to create this kind of correlation to learn. Okay, so when the image is a tiger, the brain activity should be X. And when the image is something else, then it should have a different pattern. And so this paradigm is actually one of the most common paradigms in any kind of brain utility that we have today, or brain-computer interface. And it's pretty successful. Like if we see what happens in the end of this network, and this is one of the old ones, like 7, 8 years ago. This is what the human is seeing, and this is what the network is predicting after training. This network is now disconnected from the image. All it sees is the brain signal, but it's trying to use the brain signal to predict what the human is seeing while it's getting the brain signal. And you can see that it's starting to resemble this image. So the colors resemble, the shapes resemble. And this is actually an old research. Today, these kind of research are much more advanced in how they predict things. And this is kind of the breakthrough and the systems that brought us today to be able to predict more than just the images that the mind is doing. And I'll show some examples soon. So let's talk a little bit about the data that we feed these systems and why is it so important to have a lot of data. One problem in the medical systems is that we don't have a lot of data, and the data could be a little bit biased. And so if we look at data from databases, like one thing I was working on is asking a question to the AI, what's in the background, showing it an image and getting it to answer. So this is kind of a trivial example. What is in the background? And now the answer is snow, okay? That's trivial. One thing that we researched this and we found out is that even if we show that this image and we ask what is in the background, it still answered snow. Why did it do such a silly error? The reason was that you need to look at the data. If you don't have a lot of data, your labels maybe not be distributed like you want. And we saw that the only questions that have the word background in them always had the answer snow in the data. There were not enough examples that talk about what is a background. So what did the AI learn? It learns that background equals snow. But that doesn't make sense to us humans, right? So that's a silly mistake that shows us the importance of the data that we have and the abundance of data that we need, especially in medical systems that there's not a lot of abundance of data. And so there are really interesting systems that you can actually make fail by understanding what data they were trained on. So one example, for instance, is the stop sign. We talked about self-driving cars. The special thing, you all see it's a stop sign. The special thing about the stop sign that was engineered to make the self-driving car fail. So self-driving cars that you show them this stop sign, they think it's speed allowed 50 kilometers per hour. That's not a great error to have, right? So that also shows that when we train the bigger systems, we should be aware that the data that we're trained about could be hacked. And if you go back and try to reverse engineer, you can make the system with kind of tiny mistakes, make huge mistakes. This also relates to a topic that became more and more important in machine learning called attention. And in that kind of topic, we also realized that humans rely gravely about their understanding about the world and attention. One pivotal article, a paper called Attention is All You Need in 2017 was what introduced us to the era of generative AI. And it's because the transformers that we'll come to them later on, they rely heavily on this mechanism of attention. But we realize that humans also rely heavily on this mechanism. So I'll show you a little film. Pay attention to the film and try to see if you find out all what's happening.
To test just how much attention the attention-stealing design of the new Skoda Fabia actually steals, we left one parked on this ordinary road in West London. We wanted to see if its sharp crystalline shapes, bold lines, and lower, wider profile would attract the desired level of attention. Will the 17-inch black alloy wheels stop passers-by in their tracks? Will the angular headlights attract the attention of other road users? Will a crowd gather to check out its fresh, sporty look? Well, not quite. But did the attention-stealing design distract you from noticing that the entire street has been changing right before your very eyes? Don't believe us? Have another look. Did you spot the van changing to a taxi? How about the scooter changing to a pair of bicycles? Or the lady holding a pig? Let alone the fact that the entire street is now completely different. Didn't think so.
Did you spot all the changes? Maybe some, right? And our brain is so sophisticated, how easy it is to fool it, right? So it's heavily reliant on predicting the next step, and everything that seems to us very unlikely, we just totally ignore, okay? And we find similar kind of blind spots in AI today. It's just very different than our own blind spots because it was trained a little bit differently with different kind of data. I can show more examples if you like. Some of them are related to us recognizing faces. And one anecdote about that is that we're also statistically trained to do that. So if we are from Western society, if we look at people that are from Eastern Oriental countries, they look more similar to us because we're trained on the distribution of Western countries. But the other way around is also true. If they look at us, we also look very similar to them, okay? That's hard for us to imagine, right? So that's also related to what data you're trained on and what data you're not familiar with. Let's talk a little bit about motorics. This is one of the areas that there's a lot of advancements in kind of brain-computer interface, but in AI, actually, there's not a lot. And I'll talk about why. So, you know, areas and motorics in the brain, people that study brain here know this. You have like the sensory cortex, the motor cortex, they're both here next to each other. And each area in the body is mapped to areas in the brain. They're not all the same size as areas in the body. They're not represented the same way. And they're not chronologically the same order. You can see that one area is entirely not chronologically next to where it should be. And that implies a little bit about why certain preferences exist sexually. When you look at the brain, you suddenly realize. But if you look at how the brain represents the body, it looks something like this. So you have a lot of representation for the hands, for the tongue, for kind of other areas, but it's not the same for like the body itself. It's not well represented in the brain. By the way, this picture has one big error. Can you spot it? What's the area that's most represented and most sensitive in the brain that's not well represented in this picture? Well, maybe, but I was not referring to that. That could be an error in the picture. Yeah, that's true. The eyes can be very sensitive even to kind of a tiny particle of dust. It's the most sensitive area in the body. So let's talk about something interesting. We talked about how multimodality and using all you know is very important. The brain does this all the time. It has something called synesthesia. Synesthesia is the drifting of sensation and neural activity between brain parts. And sometimes they drift between each other. And one example of that with the Professor Ramchandran, he talked about people that are missing limbs. And they have the phantom effect in which once they miss a limb, that area in the brain does not get any more signal. And so synesthesia starts. So they start getting signals from an adjacent area in the brain. So these kind of people start feeling sensations of their hand when they're pressing on their cheek or something else. And sometimes it really hurts them. So it's a very well-known phenomenon. But this phenomena, synesthesia, is something that happens to us all the time when we analyze, life. Like one clear example is these two shapes. So let's imagine that one of these shapes is called Kiki, and one of them is Mumu. Which one is Kiki and which one is Mumu? So all of you pretty much agree that this is Kiki and the right one is Mumu. Why is that, by the way? Okay, so you have some synesthesias. There's some multimodality that's happening in your perception that your visual perception is kind of drifting towards and merging with your audio perception. And that's why you feel they resemble each other. So humans do these kind of things all the time. And that's why we realize that in AI, multimodality is extremely important. And this is a pretty old video, but in the last 20 years, brain-computer interface, this is one of the biggest kind of use cases to try to help people that cannot move certain limbs to be able to move it with kind of an intervention in the brain. Today with Neuralink, with Elon Musk, this field advanced dramatically. And one of the biggest application is the motor area, to be able to move things by just thinking about it. The way this works is, again, today with AI, with deep learning. So you have the neurals fire here, and the person tells you what was the intent, so that was the example. And so it learns from these examples what is your intent while you're thinking about moving right or moving left, until you get enough examples that you can start moving it yourself. And there's a lot of experiments. I didn't want to show the monkey one. I prefer to show the humans one that consented to do this. But this is becoming extremely popular today. There's a lot of advancement in this field, a lot of different apparatus that are now in use. Two big advantages is the batteries that now don't need to be connected to a power source. And another one is the connectivity of the data. If it's Wi-Fi or Bluetooth, that you can now transmit the data to another device. And in the past, that was not possible. So these are two huge advancements in this field. And now generative AI and AI in general are very, very useful to create applications once you have this kind of apparatus. And you know what kind of function you want the AI to be able to predict by seeing the brain activity. But if talking about motorics in AI, we see some cool videos. You all seen these kind of Boston Dynamics Atlas videos of him walking, doing all sorts of somersaults, like amazing stuff. But in reality, these machines are failures. They weren't supposed to do only these kind of stunts. They were supposed to do much more sophisticated things. They were supposed to save people in a fire. That's why, that's what they were funded for, and they're failing in these kind of things. Till this date, they're not able to do these tasks, only to do these kind of gymnastics, walking, and stuff like that. And why is that? Why are they failing? Why, when I'm like looking at what they call the football Olympics with robots called Neo, and these are kind of the best academic robots that try to play football, I get bored as deaf. Like these, you can, it could pass 1 hour and you won't see even one goal. They're not even able to get to the ball most of the times. So this is the pinnacle of what AI is able to do with motorics. The reality is, sadly, yes, even though we see a lot of advancement in computer vision and in NLP, natural language processing, with motorics, we don't see a lot of advancement. And you know what the reason is? Can you guess? That's true. Do you see a lot of robots trying to walk and learn how to be in the real world? We don't see a lot of robots walking here. When you'll start seeing a lot of robots walking here, then you know someone is starting to gather that data. Until that day, we just don't have enough data. And because we don't have enough real life data, the AI here is as advanced as natural language processing 20 years ago. It's just not advancing. In natural language, we have the whole internet. And that's the breakthrough in terms of data. In vision, we also have Instagram, we have we have YouTube, a lot of visual data. So that's advancing computer vision. But in motorics, we don't have any data. And that's a huge problem. AI cannot advance today without enough data. Yep. It's not about the difference of the data, it's the presence of the data. You need to have data acquired. So I'll give you an example. Let's say you have a robot and it starts moving and it gets signals and then it falls and then it stands or something like that. That's data being gathered. And now what you can do is try to predict the next step, okay? But no one is gathering that data today. You don't have data on the internet about motoric signals. So because you don't have enough data, you cannot train an AI to be proficient in kind of these kind of things. You know how much data a human gathers when they learn how to walk? It's unbelievable how much data. We do it pretty fast, but we gather a lot of data with trial and error when we try to move our bodies, okay? But no one is gathering that kind of data with robots. And you can't kind of use a third-party resource like Instagram or the internet or videos. There's no third-party resource for motoric data that we're all gathering together. Sorry? Because you need to have a powerful need. I have a powerful need to look at Instagram. That's not, that's not entirely true, but we all have that need, I think, to look at videos. We all create tons of content, okay? And now we harness that content to train our AI. But no one has a need to see robots walking, you know? That's a video. We'll talk about that. It's not the same. You need the sensory input, not just the video. Not enough. If you compare the scale of data we have in the internet or even Instagram to the scale of the robot Olympics, it's nothing compared. It is, and they're trying. But that's the pivotal change we saw with deep learning and with ChatGPT. I was researching the same kind of models 5 years before ChatGPT, and they sucked. And then 5 years later, they gathered 100 times more data, and look at them now. So sometimes the scale is important, you know? That's always comes together. When you have more data, you have to have more computing power. You won't be able to consume so much data if you don't have that. So those are kind of the two things you have to have. Let's talk about, you said you have image. Let's talk, I'll take questions in the end if that's okay. I just a little bit conscious about our time. So let's talk about another kind of dimension that is not researched at all with AI because we're not even close to understanding how this works. So mirror neurons were discovered in 1999 by Jacoboni. He realized with monkeys that there's an area in the parietal area in the brain that responds both when the monkey eats a banana and also when it sees someone else eating a banana. The same part of the brain responds to both of them. And so he realized there's something interesting in this area in the brain, and he called it the mirror neurons, because they mirror what someone else is doing to my own body. And this is one of the most powerful things that teaches us a little bit about what we should do motorically. So the example of an image is relevant, but it's more developed. We don't know how to even imitate this with AI. We all know that small babies, if you clap or you put your tongue out, they also do the same, right? It's instinctive that we would try to imitate each other, and the mirror neurons are pivotal to do these kind of things. So mirror neurons are so developed in the mind that if I now show you just a bunch of dots on the screen, you can feel in your body what's going on. So what's the movement that's going on right now? Right? What's the movement now? What about this movement? Don't you feel this is strange? These are just 10 dots, right? And you know exactly what the movement is. So this is how developed mirror neurons are in the human mind. We have no clue in AI how to approach this problem yet, okay? So this is an example of how much the brain likes to do mirror neurons. This, this child is learning how to be a beatbox. He has no clue why he's doing this, but it's so implanted in our mind, the mirror neurons. So finally, our last topic, let's talk a little bit about language and intelligence. One of the problems with intelligence is that no one knows what it is. If you go to Wikipedia and you try to figure out what is the definition of intelligence, you find a lot of professors from psychology, philosophy talking about intelligence, and they all don't agree. The one definition that they brought 130 professors to a seminar just to try to agree on a definition, and the one that got the most amount of votes got only 51 out of 130. So that's how much we don't agree what intelligence is. The one thing most people agree, it's a bunch of functions that you can perform. So there's a lot of functions that could be defined as intelligence. There's not just one. And if you know to perform more of these functions, then you're more and more intelligent. So is ChatGPT intelligent? Well, from that definition, it is pretty intelligent because there's a lot of kind of tasks that it now knows how to do. It knows how to answer questions. It knows how to do kind of text summarization, text manipulation. It has a lot of knowledge about the world. It can solve problems. So it's becoming more and more intelligent by that definition. And that's a great kind of understanding of it, but the one thing that people, when they research it, that's one thing I did in my PhD to try to research these kind of large language models, is to try to see what's missing. So for a long time, I was able to make it fail in different ways. Long-tailed knowledge, complex questions. But today, the only thing they realized, I'm sorry about my voice, I'm losing it a little bit. The thing they realized today is that it doesn't generalize like humans. So what does that mean? They give the ChatGPT problems in math before the time it was trained, and it would solve these problems even if they were hard. And then they gave problems that were published on the internet after it was trained, and then they saw a drop in performance. So is ChatGPT merely just memorizing the whole internet? And because it's memorizing so much data, it's able to succeed? That's one thing we don't know the answer to today, because you still see a drop on data that was not in the internet. But every time I give these kind of lectures, there's an advancement. So we may, this is kind of the one final problem that we don't know. Can it generalize beyond what it was trained on? But let's talk a little bit about how it's trained. And this is kind of a slide that also talks about what we call self-supervising or predicting the next step. So the way it's trained, it takes all the sentences in the internet. There's a lot of sentences there. And all it tries to do is predict the missing word. That's all it's trying to do, okay? Later on, it predicts also a missing sentence. It predicts the next paragraph. But let's start from the missing word. So this is kind of, again, a deep neural network called a transformer. It has a lot of layers. And at the end, it tries to predict the word. When it's correct about the word, it doesn't change the weights. We talked about weights. It doesn't change the weights. When it's not correct about the word, it changed the weights a little bit towards the correct word. But how many examples or sentences like these are there in the internet? trillions over trillions, right? Like how many sentences are in the internet? And what can you learn by predicting sentences? Well, not just grammar. You can learn anything. If I predict a sentence that like this, the actor is funny or playing or acting. Now I know a little bit about ontology. I know that actors act. So I'm learning about the world. I'm not just learning grammar. And that's why ChatGPT knows so much. Because when it tried to predict these sentences, it didn't just learn grammar or how to summarize and stuff like that. It learned about the world. It learned about facts while trying to predict. And it did this so many astronomical times that eventually it got to memorize most of the internet. Okay? And for us, it's hard to grasp the amount of memorization that it was able to do. And to us, it looks a bit amazing. The other reason it looks amazing is because humans also helped it. So what happened next after it did that kind of pre-processing, we call it? They took a bunch of human annotators and started interacting with it the way we interact today with ChatGPT, giving it all sorts of tasks. And in the beginning, it started failing, but eventually it learned. OpenAI took about 50 annotators to do this for 2 years. They were able to collect millions of examples of interactions until a point it got so good in these kind of interactions that they released it to the public in 2022. But it didn't stop there. We're still training ChatGPT. Every time you interact with it, you're training it, especially people that are not paying the premium subscription. They sometimes even get choices, and then when you choose the right one, you're training the model. And so that's how ChatGPT is trained. There's no magic about it. It's just so much data and so much prediction of the next sentence or the next steps or the next response that it came to be so good that like it is today. By the way, one anecdote is in my ending of my thesis, I talked about that if crowdsourcing could help us, then we'd get to a great model. But I didn't have the budget that OpenAI had to do this kind of things. But it seemed clear to the community in the academia that this is the next step to get people. One interesting analogy, I don't know if you know the computer game Genie, the Akinator in 20 years ago, that you would play 20 questions with, and then you would predict kind of a person or someone else, and it would always be right. It would ask you questions, and it would guess what you're predicting. That's the same way. It was trained on so many interactions that it started predicting everything. So even back then, people knew that if you have enough data, you'd be able. But that was a very confined task. ChatGPT is doing something much broader. Well, understanding language in the human mind is pretty much confined to Wernicke and kind of the Broca's area. By the way, they're separated. The understanding of language in Wernicke and the hearing and the creation of language, they're not created at the same time in the human brain. It takes about 1 year apart. So kids that are younger, they understand language way before they create language. And there's the reason for that. We also in neural networks have typically, well, now it's one network, but typically 2 networks. One to kind of pre-train the model on understanding, and then kind of another model that generates the language. But one interesting thing is we come back to synesthesia. Remember, 2 kind of sensitive coming together. So try to read what's on the screen here. So most of us are able to read this, right? Are you amazed that you're able to read this? You know why you're able to read this? It's because you have semantic understanding of what grammar should look like and what the topic should be. But also visually, this rhymes with what your eyes thinks should be visually. And so they both come together to try to solve the problem. In AI now, OpenAI GPT-4o is a multimodality model. So it combines vision and understanding of language at the same time, and it was trained on both of them. So when I ask it to try to figure out what's in this sentence, it also solves the problem. This is one pivotal change that AI is going through right now, multimodality, towards being able to use everything in our knowledge to solve problems in the world. Let's talk about brain-machine interfaces here. There's also a lot of advancement. This is also not a very new video, but even in audio, neural networks are now helping us decode what the mind is doing with implants. So what the person is doing here is thinking about setting a sentence without saying it, and then the AI needs to predict what it's trying to say. And you're seeing the result here of the prediction. So, and this was 5 years ago. I'm sure today there's like much more advanced researchers about this. They all talk about deep learning and AI and getting enough examples to be able to predict all the text and speech. So let's talk a little bit about language understanding in the mind. So I said that language understanding is only in Wernicke and Broca. That's wrong. Language is all over the brain. We understand language and it's mapped to the whole brain. This is kind of an experiment that they did with people in fMRI, a brain scanner, and they read stories to people and see which parts of the brain are activated when they hear a certain word. And you can see that the whole brain is activated. The reason being is something called grounding. Generative AI understands only text. Now it understands images, but we understand more. We understand the physical meaning of the world. If you ask ChatGPT what it feels like to eat a balloon, it would not be able to understand this sensation. You would feel, what's the taste of the balloon? You'd say it's probably bitter, right? It's not sweet or something like that. But that's because when we were babies, we really grounded everything. We touched everything. We have that kind of knowledge. Now, nowhere in the internet it says that a taste of the balloon is bitter, because who would say that? So, because it just is common sense and people don't report the common sense. And so grounding is in the brain, and when I tell you, for instance, think about a hammer. What part of your body you start feeling? You feel your hand, right? That's why a hammer is grounded to be a tool. And so it makes the motor area operate automatically. These things happen without me asking you to use a hammer. You just feel your hand instinctively, and your area in the brain that talks about that tool lights up. So you can see that here, like talking about an apartment, house, parking, all these kind of related topics are in the same area of the brain. That's the grounding of those areas. And there's this common saying, we use 10% of our mind. That's bullshit. Like, we use our whole mind, and you can see that. Everything is grounded in different areas of the mind. So this research, by the way, is called the Brain Dictionary if you want to see which word is mapped in which area in the mind. So finally, let's talk about our last topic, memory. Well, in the past, people thought that memory is an area called hippocampus. Hippocampus looks something like this. It looks like the animal hippocampus in the sea. It's a limbic area way inside the brain. It's a very ancient area. And they thought they're right, but that's a little bit similar to the physics researcher and the grasshopper joke. So the reason they thought the hippocampus was the memory area is because each time the hippocampus was injured, people would not be able to produce long-term memories. But that's like thinking, there was like this joke about a physicist trying to understand where does the grasshopper hear. So it clapped their hand, the grasshopper hopped. Then it took one leg off, then the grasshopper hopped. 2 legs, 3 legs, 4 legs. And the 6th leg, it didn't hop anymore. What's the conclusion? What's the conclusion? What? Yeah, it hears from its legs. That's the same conclusion as like memories from the hippocampus. Because the hippocampus is injured, you don't create memory, so it's there. That's entirely not true. Memory is also in a lot of areas in the brain. We have motor memory in the cerebellum. We have medial temporal lobe memory about all sorts of memory is about long term. We have the amygdala that is emotional memory. Prefrontal is about facts in the world. So memory is across all the brain. And the reason I'm mentioning memory is because today in AI, we know how to replicate a lot of memory types. You see here different types like sensory memory, short-term memory. Implicit memory is like memory that like we learn how to walk or how to do a motoric thing. It reinforces our memory until we know how to do it automatically. That's implicit memory. The only thing AI is missing is what we call declarative memory. So what we saw here, the neural networks, they're all about implicit memory. So the memory is implanted in the neurons. Declarative memory is memories that you can create in a moment. You don't need a million examples to create them. You know, there's some memories that you just tell me something and I memorize it, and I'll remember it forever. That's not how neural networks work. That's a different mechanism. We don't know how the mind does this. We're not able to replicate this with neural networks. So what happens is we use the computer memory to be the memory of the neural network. So today, the next phase of neural networks and machine learning is these kind of models that talk about chain of thought. This is using our neural network, the language model, to feed itself. Meaning, if you give it a complex task, it would output first the plan, then it would output the first step of the plan, then the second step. So it's feeding itself. Every time it's outputting something, look at it, what it's done, and then continuing from there. And there are different ways to do this. Chain of thought is it trying to solve a problem in iterations. And if you've seen the new model by GPT-01, it does exactly chain of thought, and it tells you what it's doing. And it runs the neural network in multiple steps. React uses external tools. That's like the memory. It can ask the internet a question, get the answer, and continue processing. So that's called React. And there's many, and WebGPT is what you see today with ChatGPT. Sometimes you ask it a question, and it goes to Google, and then it comes back with the answer. That's WebGPT. It's going to its environment and coming back with the answer. This is kind of the future of neural models, and you see that more and more with OpenAI. And the reason I'm saying in the title that it's one step towards consciousness is if you think about a neural network, it's a little bit like our subconscious. Sometimes we think about something like a name of a person, and it pops, right? And we don't know how it popped into our mind. That's a little bit like the neural network. It gets the result, it was trained to do it, we don't know how that happened. But the consciousness, it is what actually fuels this kind of reasoning. So when we do a multi-step kind of math problem, we solve the first step, then we memorize, we look at it, then we solve the next step. And we feel the consciousness is us solving the different steps, not us getting to the to the answers of the intermediate steps. That's like the subconscious working when we do that. So again, that's just my hypothesis, but I think this is one more step towards consciousness. Finally, a little bit about what Ask AI is doing. So we're trying to bring this revolution to the industry so that every kind of repetitive task that you do, you can now use all your company data with the AI to try to solve it. So this is just an email that talks about many questions that need to be solved from company data. And now you see the AI helper going to all the company data, bringing all that and just answering your email in one shot. You can imagine that when you get a questionnaire in an email with all sorts of questions, it takes you time. The AI can save you all that time, and then you just copy, paste the answer, and you're done. This is just one task that you can solve with bringing AI and marrying it to company data. And that's what we do with Ask AI. So I hope you enjoyed this kind of lecture. It was a little bit all around, but I hope it gave you a taste about kind of the intersection between AI and the brain. Thank you.